It's also about 1/3 of the book that I have coming out next month is about biological metabolism and its potential application to cultural evolution and to the evolution and development of new cities. So tonight is going to be a kind of summary of what metabolism is, how we understand it, all the kind of weird and interesting, fascinating forms and mathematics there are in biology, and what the potential is to use them for the analysis of existing cities and the design of new ones. Inevitably, that conversation involves a little bit about climate, a lot about evolution. So I hope you enjoy it. Tony is going to try and keep me down to 1 hour, so I'm trying to go quite fast through a very big subject. And I'm happy to have conversations with you afterwards about more detail. Okay, what we're talking about is form. And the architectural understanding of form is quite limited. We think in architecture, form is the kind of outside boundary of a building, a mountain, some kind of object. Form in biology means something quite different. Form in biology is only persistent for a singular lifetime and yet persists through thousands of generations. And form is the product of the flow of energy, material, and information. And I'll do a little more detail about that. That's the first kind of very big difference in this topic, is understanding what form is to biologists and to those who work in complexity. We also need to understand the thermodynamics of the Earth. And everything that I'm going to say from now on follows from that. How energy falls on the Earth, how that pattern of energy is irregular, subject to many variations, that produces differences all across the Earth, and those differences are not stable either. And you and I, human form, evolved under those unstable conditions, and every form that we see on the Earth, every natural form, did too. So this is just a little bit of the context of how that heat and energy is moved around the surface of the Earth. Most of you will know a little bit about this, and another time we can do in more detail. Essentially, there are three kind of patterns that intersect. One in the atmosphere, and you will know when you're cooking, you hold your hand over the stove, the hot air is rising, and there's a very strong structured pattern to that. But that's kind of confused and distorted by what's called the Coriolis force, the spin of the Earth. And on top of that, the thing that's been affecting us all over Europe in the last weeks are these very high jet streams that form at the intersection of these circulatory cells. And the ocean does something very similar and has its own sets of patterns that are related to that. And this is the first bit of interesting maths. I'm not going to do too much detail, but you can see in this little summary diagram the scales of variation that we're talking about. And these turn out to be very significant. 11,000 years and about half of that. That's more or less the age of human civilization that's normally presented in architectural histories. And I'm going to extend that rather more and show you a little more about how that works. Okay. So, back to forms. Forms are always coming into being. The system we're most used to, the complex system we understand most, and most of our lives are tuned to, is the weather. And then if you think about it, it's very simple components. It's really only air and water. And yet, all of these, and these are just a few of, I think I have 30 different categories in another lecture I will show you. These are all variations of form. But it's the same chemical material. It's the same stuff. What changes is the flow of energy through it, and what also changes is its immediate context. This and this, those of you who come from arid climates, these are close-up of snowflakes, and these are hail produced by the same process. just kind of up and down, a little more up and down will produce this. These are very interesting, really odd, very rare, called ice flowers. This needs a tiny difference of temperature. This water, as you can probably just see in that photograph, is just on the point of freezing. The air is cold, well below freezing. And that produces these forms. They're very temporary, very beautiful. Most of us know about these. So what we're talking about is a continuous process of complex systems. Part of my argument that I won't go into in detail is that cultural evolution is a complex system. Culture itself is continuous. It's always modifying. Like biological systems, it has no goal. There's no end game. There's no stable state. So the other point that I want to make about forms, generation of forms, complex systems are always subject to variation. There are no equilibriums. We think of things as stable, as equilibrium, because of the scale of our lifespans. Mountain is more or less the same shape today as it was when I was a boy. And pretty much we judge everything in relation to our own lifespans. If we look closely, every natural process, it's always subject to very small oscillations and sometimes extremely big ones. And in terms of metabolism of cities, I'm going to be talking about the big ones. Most of the forms on Earth have been strongly affected by humans. Not just in the since the Industrial Revolution. I'm not making that argument. Humans are approximately this, what we call an anatomically modern form, is approximately 135,000 years old. But the evolution from the great apes, which is strongly controlled by a metabolic system, is more or less the same age as the civilizations here. It's more or less the same age, as the mountain forms and the land forms. So humans, their evolution from the great apes is approximately 2 million years. If you went back beyond 2 million years, these land forms, these deserts, river deltas would be quite different. Okay. This is an eroded mountain. So the oldest continent on Earth is Australia. This is in southwestern Australia. This is what happens to every form. Every natural form comes into being. Some that last millennia, like mountains, still break down into their constituent materials. They collapse and they reorganize. Those materials go somewhere. Most, not particularly of this one, but all of this is produced by what's eroded off that. So just like the weather systems moving heat around the Earth, there's also a movement of material around the Earth. So you can see a very clear, there's a very clear relationship between those. And we can do some of the physics of that another time. Okay. So now we're coming to trying to define what metabolism is. All living systems have to capture energy. That's what we share with every other living thing, from a microbe, tree, blue whale. We all have to do that. But more importantly and more significantly for the design of cities, we're used to other people capturing energy for us, but we have to transport it, and we have to convert it or burn it in some way to maintain ourselves. And there are two models that we can look at for that. Traditionally, the architectural knowledge of metabolism, as far as it goes, which is very slender, is more or less worked around mammalian. And if we look, just like you and I, we are mammals, we maintain a constant body temperature, and we burn a lot of energy to do it. And we do all that inside. These guys probably are more significant for us because they, and I'll go into a little bit of the maths of this in a minute, but they get most of their heat from outside. And the consequence is quite severe and quite appropriate. So these guys, well, I hope that's on the next one, can convert about 10 times as much of their food to body mass as we can. Nearly everything we eat, we use up. If, like me, you eat a little bit more than you need, you tend to be... I have this thing with pastries, it's a bit of a problem. There's some very weird maths in this, kind of weird and fascinating. And I'm just going to give an outline of it tonight. But what seems to be critical is the body mass, the volume and the weight. Every living thing has a metabolism. And nearly all aspects of living things relate to their body mass. And no matter what the organism is, whether it's a blue whale, an elephant, us, or a tiny mouse or a shrew, the tissue, what it's made of, in its lifespan, gets through the same amount of energy. And that's really weird because, elephants live 60 to 80 years. Nobody's quite sure how long the largest whales live. We know some reptiles can live 150 years. We know trees that live more than 3,000 years. Nonetheless, they use up, in their lifespan, each gram of tissue, the same amount of energy. How does that work? Okay. It's to do with how fast they use energy. Okay. Those of you who've seen Blade Runner will know what I'm talking about. Short and beautiful life, you use up a great deal of tissue. So this thing lives very fast, we can say. Okay? This thing lives very slowly. And that's why they're different sizes. So that's the first kind of set of principles that are mathematically defined that's useful for us. Biologists call this allometry. So allometric relations are really crucial and very appropriate for architecture. So the lifespan can vary. Bacteria, a few hours. I think a mouse, probably 3 years is generous. Nearly always they're 2 years. These a little more, 60 years. And of course trees, a great deal longer, although their processes are rather different. Okay. Metabolism has been called the fire of life. Without metabolism, there is no life. There would be no natural forms. There would only be mountains and rivers and deserts and so forth. Okay. And metabolism is very strongly coupled to the anatomical organization. It's also coupled to all sorts of weird and interesting dimensions within your body, the size of your aorta, the number of heartbeats per minute. And these turn out to be very significant, and the mathematics of this is very well known in biology, very well documented. Okay? Lots and lots of published papers. Unlike architects who tend to work like this, and we don't want to show anyone how we did anything, we just show the kind of finished thing. In the sciences, and particularly biological sciences, it's the other way around. You can't have a result and show it to people without showing how you got there. So all of this is available to us. It's transportation of energy from its source to every single cell of a living system. And what they require are surfaces and branching networks. Surfaces and branching networks I'm going to talk about in relation to that. And that seems to be true across all scales that we know about. And these are some of the other things that scale also in relation to body mass, how fast the fluid flows, the cross-section of the aorta or the phloem vessels in case of plants, the number of heartbeats, and there are many other things that conform to those power scales. Okay. So branching and surfaces is the kind of physical architecture of how energy flows through living things. It's also, if you think about it, something that as architects we naturally think of in terms of cities, designs of buildings. It's a relation, we hope, of branching networks and surfaces. Okay. And this is probably the most profound, or at least in my view, profound piece of mathematics that's happened in the last 15 years, at least in terms of its effect on architecture is by these three guys, one of them a physicist, one a biologist, one a kind of systems expert. And they've done the maths of these branching networks, and there are three constants in that, but pretty much is visible in their kind of very simple diagram. Some of that we would know intuitively. If you take a tube and divide it into two, pretty much you know, you try and make those two areas add up to that area. Okay. And you can test this. You can model it yourself. We've done a little bit of that in Emtech. Some of these things are too complex for most laptops. But pretty much these organizations, shall we say it's architecture, its arrangement of material in space, comes from its metabolism. It's not that the metabolism is applied to a form or a structure afterwards. You cannot have them separately in biology, in living things. The form is a product of the metabolism. And pretty much, although they don't look exactly the same, mathematically they are the same. So even though we can say, oh, well, this doesn't look quite the same as the fan coral or the tree, in terms of the mathematics of the branching ratios and the velocities of flow, it turns out you can define this in the same way as you can the others. Okay. There's something else that comes out of that organization, and that's the relation of things, living things to each other. So the distribution in a forest of how many really tall trees, where their canopies are, how many small ones, the kind of pattern and logic of the relation of individual trees to each other and their distribution is also a metabolic system. It's a product. And you know, if this is absolutely, healthy and vital and enormous, they're not going to be very tiny ones growing underneath it. But this has a definite lifespan, and these things, cavities open up and they're colonized, not always by the next largest one. So there's fixed ratios in these things that we can use very directly when we're thinking about cities. We're not quite advanced as that. There is no mathematics in cities for the relation of the number of big buildings to little ones, medium ones. There's no set patterns. We have other kinds of ways of patterning it, mainly cultural, streets, paths, neighborhoods, blocks, all that kind of stuff. You're all very familiar with that. But there's an enormous amount of work and a potential to apply this. Okay. Metabolism has a way of helping a form to adapt to a different climate. There's no standard leaf. There's a standard skyscraper. There's a standard medium-rise apartment block, which you'll see in every city across the world, regardless of culture or climate or economy. But in nature, there's no standard leaf. Everything is adapted, metabolically adapted, so its form is a response, it's change of form, to a particular climate and to its particular ecology, its forest, or where it's living in relation to other ones. So these are very interesting. You're familiar with these. Cold weather adaptations, hot weather adaptations, and they produce a great variety of form. But these are essentially driven by metabolism. Okay? The ability to capture energy, sometimes in this case capture water and store it, little degree of self-shading, coping with some of the extremes of climate. This kind of quite architectural thing looks little bit like the GLA building, but it's got some extra stuff on it. But actually this is a lot smarter. This can change shape. When there's a lot of water, it can collect a lot of water, it can get really fat. Yeah? It can expand itself, it can sit there all nice and squat and full of water. It will store that for when there isn't much water. When there isn't much water, as these start to change and shrink, the degree of how much shading it's providing for itself increases. As the water is lost or used up for its living processes, it can increase. The effect of that is a geometrical change that will increase the amount of shade that it's casting on itself. And some of these are kind of totally weird and quite fascinating because of that. Okay. We have a lot of surfaces in biology. I'm going to show a couple of slides of exterior surfaces. But nearly everything I showed you, like the images of the human lungs and so forth, and if we think about the kind of nasty stuff on the inside that's processing all the food, capturing and burning and making energy for us, it does it through surfaces. And nearly all of that interior organization is to increase surface area. Somebody once told me, and George will tell me if I'm correct, that if you take a human intestine and stretch it out, I think it's over 20 meters, but it's packed into, an area a bit less than a meter. But actually, if you try and unfold it that way, not just stretch it out, look at its surfaces, you've got something bigger than a football pitch, bigger than 100 meters by 100 meters. So metabolism is about the organization and packing of surfaces into volumes. And you think this obviously has a severe and interesting implication for cities. Skins are also adapted. This guy, of course, is heavily armored. Part of that is just protection. It also has to be waterproof, a lot more waterproof than you and I. And it also has to have a degree of kind of thermal insulation, and it has to be able to adapt that, and I'll show you a little bit more. Our skin, of course, is quite different. We have other kinds of metabolic we have other kinds of climatic problems. We generate all our heat on the inside. Most of the time, unless we live in the far north, or unless we've been working all night and only had coffee and nothing to eat, most of the time we're warm or too warm. And we have to get rid of heat. The little beads of sweat you can see on that. Okay. Some cold adapted animals have fantastic insulation. And it's not just like we do in architecture, where you can just pile up a thickness of, I don't know, what do they use, wolf? Fiberglass or rock wool or whatever it is. But it's organized in such a way, this guy, as you can see from this thermograph, these are the only places where it's shedding heat. Everything else is doing fine. There's no heat escaping from here. But in the summer, this guy's got to get rid of heat. That insulation is no use to it in the summer. And it's an adaptable insulation. And George has a number of very good lectures of that. But partly it does it by these very fine structures. This is within the hair. Partly it does it also by being able to turn on and off vessels inside the fat. Horrible thing to talk about, fat. But, we all have it, bits of it, some rather more than others, regrettably. But what we have is kind of like solid fat. We can't do anything with it. But a lot of very cold adapted animals can shunt blood through their fat. They can change its thermal properties. They can change something from being super insulin to only a little bit insulin or not insulin at all. Nothing like that yet exists. Okay? If we look at this guy, he's got the opposite problem. Right? And you can see the only kind of cool bit on this guy is the ear, and this is what that's doing all the work of cooling the blood. Right? And the same with these guys. Okay? You can see those are the only hot spots. I don't know that any animal has ever solved the problem how to stop heat loss through eyes, except by shutting your eyes, I guess, or through here. But pretty much they've solved everything else. So there are kind of stuff we can do, and we can learn from that. We can learn from the principle rather more than from the particular mode of insulation. So pretty much we all know, those of you who are interested in sustainability, there's been an awful lot of work done on how to make buildings really, really much better performing in different climates, but every advance they make seems to throw up a new set of problems. So the GLA, for example, global form was optimized to minimize heat loss. We all know a sphere has the best ratio of surface area to enclosed volume, and it was great, and it could conserve a lot of energy, and they forgot to think about the other way around, what happens on hot days in the summer, when you've got to get rid of it. Okay, so the kind of engineering side of individual buildings is quite well advanced in some ways, but in a kind of mono direction, not the kind of fluid exchanges and metabolic systems that we see in nature. Another thing that comes out of metabolism are mutualisms. Another set of mathematics very interesting and very good processes about that. And there are many different kinds. There are parasitical ones. There are ones that are kind of fairly neutral, like bromeliads. Orchids, they don't do any harm to their host, but they don't do any good either. And then there are some that neither can exist without the other. And I'm going to show some examples of that. I've talked a little bit about that. So these two guys need each other, not only for protection. This is also doing some cleaning actions. And you will see in some extreme cases, they cannot exist without each other. Okay. Each one of them has evolved. So the processes of how they capture, convert, and transport energy depend on the presence of the other organism. So those two metabolic systems are coupled. Neither can really exist without the other, and they evolve together. Spatial organizations come out of metabolism, or metabolic relations between living things. This is not one single organism, this is actually a colony. And they organize themselves in this way. There's nobody telling them to do this. This is probably, these are very simple creatures. They really consist of a kind of mouth and an anus and something in between. And they organize themselves into this kind of structure, although they're all individuals. And this maximizes their capture of energy for them. Okay? Much more efficient than one of them with their tiny little mouth to try and use all of this to capture their food. And some we know are very complex in terms of their geometry, also their material processing. And what's super amazing about the social insects is that they can regulate their interior environments to within half a degree. As far as I know, there is no known human system in any building that can do that, to that degree of fine control. But they're also simultaneously regulating the percentage of moisture and many other kind of related factors. Okay? So metabolism is the principal organizational system that produces this form. And there are many variants, but pretty much they're all, shall we say, material artifacts that are produced to enhance the metabolism of the collective. Not so much the individual, or each individual benefits, but it enhances a collective metabolism. A place to store food, to bring up the young, to propagate the next generation. And they have very, very fine controls of these. Now, some of it sounds very crude, and you think, well, surely engineered systems are going to be better because we have micro switches and transistors and nice circuit boards. And if they want to modify airflow through here, some bee's got to stick its ass in the hole. Okay, so we think naturally humans have got to be superior to that. And yet none of our systems perform as well. None. Nor do we have systems that optimize for several parameters simultaneously. Some forms are really elaborate. If we think about the scale of an individual termite, it's about the size of my small fingernail. It's got no brains. I think it's got 8 or 12 neurons or something like that. But they produce, so this, for a termite, is a skyscraper, at least. Maybe even kind of, pretty big one, pretty damn big one, or it's a group of them. And they regulate everything. But no single termite knows how to do anything except what its immediate neighbors are doing and its own little patch. These are what are called magnetic termites. It's not because the termites are magnetic, but these are always aligned east to west. And there's various arguments about it, whether they're sensitive to magnetic fields, but it turns out what they're really sensitive to, one side of this is warm. You can see this is facing the sun, and the other side is cool, and they have this kind of exchange between the two sides. And these are the more ones we're perhaps more familiar with. Now, more recently, architects have often said, yeah, we're doing stack effects, we'll have a central chimney, and it's based on a termite node. And what it turned out to be, it was based on a 60-year-old diagram that in the last sort of 10 to 15 years has proven to be totally wrong. So all this stuff that people have been saying in architecture about imitating or the biomimetic, learning from termite strategies and termite nests, was totally wrong. And what turns out to be significant, we saw a project earlier today, it has a lot more detail, is the relation of these kind of small turbulences on the boundary layer and the movement of moisture through the system. And they do not have central chimneys. And what they manage very well is this kind of what they call metabolic buoyancy. They can move more water in, they can move water out, they can take the water, kind of chew it up with some of their stuff and deposit on the outside so they get some evaporative cooling on the opposite side to the turbulence, and they make use of their environment. And yet, no termite has a brain. Okay. So what we can say, out of my argument, intelligence and spatial organization and material artifacts emerge from the collective metabolism. And this is very significant and important for us as architects when we're thinking about cities. The other thing that's really interesting for those of you into evolutionary computation and want to follow on that line, the ability to do that is genetically conserved. That is, your termite nest is not quite as good as yours. It's more likely that your descendants will propagate new good nests and your descendants will not survive. So there's an evolutionary mechanism that has enhanced that. And the fact that it's taken maybe 3 million years to do it is not really our concern, because we can simulate that in a computational environment. Wolf's looking disbelieving, but we can. Okay, but probably this top sentence is really crucial. Now, what follows from that is there's a kind of topological organization. We're going to move very quickly to human organizations, and I have topological diagrams in relation to that. So there's no hierarchy in the social insects. And pretty much they have a centrally organized artifact or construction, and they have a kind of territory around it which has some boundaries, and everything they're moving from outside to inside. Okay. So most of us, I hope this is not offensive to anyone in terms of religion, but pretty much we all know this kind of story of the evolution of humans from the great apes. What's not often described is how culture is wrapped up in that evolution, and climate and ecological relations. And part of my argument is if we understand how this evolved, this fantastic, well-organized, beautiful form, in relation to culture, climate, and ecology, we will understand how to deliberately direct cultural evolution for new kinds of cities. Okay, so this is the spatial organization of the great apes. They're not random wanderers through a territory, which you might think. I thought before I started to study this. They do have a hierarchy. They nearly always have a leader. Actually, quite often they have two leaders. There's a big alpha male who thinks he's the boss, and there's some senior matriarch who's keeping him in line. And it's funny how often that pattern's repeated in nature. Okay. And they move in a quite ordered way around their territory. And what is the order? The order comes from the seasonality of their food. It's a metabolic logic. They have a material culture. They do make nests, not very elaborate ones because they only have to last 2 or 3 days. They don't have a particular spatial organization that's interesting about their nests, but the way they group them is in an approximate circle for defense, where they're young and kind of vulnerable in protected areas. And more importantly, they teach their offspring. This is the start. This is before us. This is what we came from. The transmission of knowledge through time parallels the genetic transmission of information through time. And they have material structures. Okay. The other interesting thing is, how did we get to have this kind of big head? Because metabolically this is extremely expensive. It's a lot of a problem. It's approximately 22 times, it uses 22 times more energy than the rest of your tissue. You all know that, those of you who had submissions today or in the last week, and you worked a couple of nights in a row and you're struggling to stay awake now, right? It's because you've been thinking. Thinking is the most metabolically expensive thing you can do. And that's had a profound effect on the organization of our interior surfaces and our general anatomy. And it happened with the evolution of this stuff. Humans became efficient killers, more efficient than a single animal because they learned how to hunt in packs, and they used tools to kill things with, cut them up, and they learned how to cook. Well, right? Cooking turns out to have a major impact on human anatomy. So the transformation from, let's say, the middle part, the hominids, to anatomically modern humans comes with 2 effects. A lot more density of energy packed in the food through cooking. Yeah, it contains a lot more. You can process a lot more. And a very big change in the interior organization of the gut. So ours is very different shape, different densities, and so forth. Okay. Around about 35, this is slightly debated amongst, there's a different argument presented by archaeologists and presented by cultural evolutionists and by anthropologists. But more or less it's known around about 35,000 years ago, humans started making more elaborate structures, more or less about 35,000 years. And pretty much they were like this, holes in the ground with some kind of covering. It's speculated they might have been animal skins. We do know from some remains, and I'll show you. And there's a variety of forms and organizations that have been found for those. So humans, all modern humans, originate here. There's a small population 135,000 years ago, anatomically modern humans. Everyone on Earth is descended from them. And there are some biologists who argue that everyone on Earth is descended from one woman in that population. And she's known as the mitochondrial Eve. So genetically, we are very close. All the stuff we have about different cultures, different races, and all of that, all of that's really recent. About 65,000 years ago, and the date is not arbitrary because it's a moment of great climate change in this region, humans started to migrate. And more or less this is what's called a consensual map. It's the one map that nearly all biologists or linguists or anthropologists agree on. There's lots of variations. There's lots of ones who argue there are several pulses, but these are called out of Africa maps. This is very significant here. In the US, they tend to dispute this date. I'm not quite sure why. some of the arguments they put forward is it can't possibly have taken only 1,000 years to fill up all that space. But actually, mathematically, when you do the maths, it can, because what they counted as full up, what is a mature, fully occupied system for what they call the hunter-gatherers, is actually really, really sparse population. It takes a lot of space, a lot of land, a lot of living things, and a lot of territory to support one human in that system. Okay. And we can see, if we can compare some of these factors, I won't go through the whole thing because you'll go crazy with boredom and some of you will fall asleep, but pretty much when we look at Homo sapiens, that's us, sapiens sapiens, it should be, but there wasn't room to put that. Okay. We're pretty similar. We have similar kind of troop sizes, more or less community sizes. Pretty much everything is very, very similar here. Okay. The density is really interesting. The hunter-gatherer societies, or hunter-gatherer fisher, because they did a lot of fishing too, were pretty much fully spread over the whole surface of the Earth. So for their society, the Earth was full about 12,000 years ago. Full. Maximum population that could be supported by those things. Apart from Antarctica, no humans there. Okay. And still we have some of these traits. They do say the maximum number of humans you can relate to is somewhere between 150 and 200 that you can know by sight and acknowledge, which is pretty much the same as an ape. So some parts of our evolution haven't gone a lot further. We still have many social organizations the same. This is 35,000 years ago. Culture was fully assembled, at least all its elements were fully assembled 35,000 years ago. Graphical arts, and these are not religious, but these are data sets. The reason some of these are drawn very large, it turned out that they find a huge number of bones very close to these paintings. This tells you the relative size, how many of these kinds of animals are around in this territory, and pretty much if you follow these kinds of things, how to kill them. We have efficient tools 35,000 years ago, and we have at least lunar calculations. We know about the weather, we know about the ecology, and we know how to count, and we know how to keep records. That's the basis of culture. It's an ecological, metabolic basis to all culture. That's where it originates from knowledge, ecological knowledge that's for your metabolism. And that's fully assembled 35,000 years ago, and we start finding from then on more and more elaborate variations of these. And pretty much they occur consistently with some regional variations, as you'd expect. Well, you wouldn't expect that nowadays, but then the particular shapes and forms were adapted, but pretty much they all exist within this latitudinal band. You don't really need them here. You just need something more temporary. It's a lot warmer. You only need to keep dry occasionally in these regions. And that's why humans can spread. They could kill things, they could make clothing, they had artifacts, and they had the ability to adapt those artifacts to different climates and to different ecologies. Not something we do terribly well now. Not yet a city, but starting. These are aggregations. We find these ruins. You can see the scale here. They're very small. And what we see are these kind of cluster organizations. In the beginning, some people argued, well, it's just a leftover space. But there are central circulation spaces. Some kind of social organization is producing these configurations. This is 22,000 years ago. Absolutely amazing. These are mammoth bones. This is the scale of pit structure, and this is what they used to build the above ground structures. Every continent argues that they didn't kill the megafauna. Okay? If you're in the US, it's some terrible catastrophe. If you're in Australia, the Americans and the Europeans did it, but we didn't. Every culture says that. Nonetheless, between 35,000 years ago and 22,000 years ago, these guys became extinct. And their bones are found in every human structure. And some things are very smart. I mean, really architectural. You know, this kind of, nowadays you say that's a component system. You could do that in Grasshopper, right? You'd model one of those, do your little circle, kind of wrap it around, do it this way, and you've got a structure. Okay. Very smart. The other thing really smart is they knew how to cut a bone and put a wooden post in the cavity. So they knew how to protect the wood from rot at the bottom. They had paving, and you can see some of the remains here. This is in England. And they had these kind of quite large aggregations that they start to accumulate them into larger and larger structures. The other thing that goes along with that is the evolution of what we call a longhouse. So these are modern recreations of the more evolved forms of pit structures and of the longhouse. So gradually they stuck all these small ones together. At Kostok in Ukraine, they found 12 of those little circular ones all in a row with 12 individual hearths, but it's one long space. Each hearth would be one family. So you're talking about, you know, kind of beginnings of kind of larger scale architectures that arise out of the same thing that drives the social insects. A way of externalizing some of your metabolic problems. Okay? You don't have to eat more food if you can manage to damp down exterior variations of climate. Okay. If you can cook your food, then you have, you know, more enhanced kind of packing of energy. And actually you still find, this is from Iceland, it's a recreation, but in Iceland they argue, or more or less until the 19th century, these kinds of course they have stones up there and so forth and not much wood, but still this is a very evident, simple evolutionary step from the things that we've already seen. Longhouses in various forms are found all over the earth. The first town halls in England, those of you who are kind of used to that, looked at kind of evolution of medieval houses and so forth. Every culture has some kind of longhouse, sometimes associated with very strict social organization. So in Malaysia, these parts of the world, there are very strong rules about who can sleep where. The animals are always underneath. And because these forms are temporary, they're also often encoded in religious practices. Anyone who grew up in Japan will know a little bit about that, and parts of India. Each component has a name, it has a season, it has a time when it has to be rebuilt. So for example, most Japanese temples, the form is permanent, that is, it persists through time, but it's regularly rebuilt. And it's not very rarely rebuilt all in one go. Fragments or pieces are rebuilt, and those are encoded and matched to certain seasons. So it's a kind of development of that ecological base of information and knowledge that regulates our metabolism. If you combine these two patterns, you get the patterns of the first human settlements. What I don't call them hunter-gatherers because I think that's rather misleading. It's the founding system of civilization. Essentially, this is an externalized metabolic system. You tend to get a large pit house or longhouse set of structures that are more or less permanent. They're not always centrally located, as in this one. And you have a series of seasonal hunting camps or gathering camps, and you have a pattern of movement that is structured by climate and by the different seasons and the availability of food, also by the tracking of game and so forth. And you start to get links between each of these territories. Just like in the apes, males go to the boundary, they want to attract females from out here, and of course the females do really want to be attracted, but they don't always want to say so publicly. But, okay, so there's a genetic exchange across these boundaries. Right? You also get trading networks. You find obsidian blades from 35,000 years ago that are thousands of kilometers from their source. Thousands of kilometers. It's absolutely amazing. And it's just moving through these little tiny patches. Well, they're not that tiny, because the other thing we need to recognize with these things in this system, when we think of it as a system, the amount of territory you need to support a tribe, let's say a little clan of 150 to 200 people, is something like 1 kilometer, 1 square kilometer per person, somewhere around that. This system evolved to its maximum capacity. Its maximum capacity to support its population. And that turns out to be very significant. Humans have always done that. And actually almost every animal does it. And even trees do it. And microbes do it. So it's not unnatural. It's not the fault of humans. Okay. And what happens when it's at maximum capacity? It's very sensitive then to any change in climate. Climate change will produce a change in ecology, the amount of food that's available, more significantly, not just the quantity, but where it is and when it is. And those patterns, if we think about this just in terms of complex systems, tend to collapse. And there's 3 possible outcomes of collapse. I'm going to come back to this at the end of the lecture. Okay? There's dispersal. You have to go somewhere else to get food. You leave where you are. In terms of cities, this turns out to be, in the past, very significant. There's simplification, lower level of complexity. I'll talk more about that later. And there is complexification. So cities emerged from the collapse of the founding system, from the collapse of the hunter-gatherer fisher societies. They were at their maximum capacity. You were taught, probably the same as I am, that more or less since the ice age ended, the climate's been the same, stable, equilibrium. If you read climatology, that turns out to be absolutely untrue. Not only a bit wrong, fundamentally wrong, by a big order of magnitude. So between 6,000 and 5,000 years ago, somewhere around there, cities emerge in 5 separate locations, more or less simultaneously. And there is no human that even in 1,000 years in those systems could move from here to here. It's possible, you might say, well, maybe cities started here or here, and they gradually moved around there and went that way. Humans walk, if they're going on very long journeys, and if they're taking their families, about 2 kilometers a day max. If they're with livestock, probably only 1, and most of them get tired. And no single human in those days ever made the journey from there to there. But there were waves of expansion. Everybody moves a bit, and the people who are there, more people come, and they move on, and that's how they go. Okay? And it's not, these are also now, we know them to be the arid places of the world. But they weren't 6,000 years ago. If you look at aerial satellite imagery for the Sahara, you can see under the sand all the river courses. If you read Cicero, even in the Roman days, there were large stands of trees, there was flowing water, there were lions, there were all kinds of animal life, not desert as we might think of it now. And the same is true here and of all these places. There was a profound climate change. And the same thing that's beginning or about to happen to us. Climate change either involves getting warmer or cooler, but the effect is to move the pattern or the distribution of rainfall. If we think back to that earlier diagram I showed you, those big cells that are carrying the hot air up and they're carrying moisture up, and when they cool they start to sink down. Where it sinks down tends to be in a different place. And we've seen some of the effects of that this winter. We've seen a lot of those things. So it's not just about things getting warmer or cooler. The most significant thing ecologically is the pattern of rainfall. And that pattern is subject to profound shifts north or south. And that's what happened between 5,000 and 6,000 years ago. It's very well documented. 3 successive periods of drought, each lasting between 150 and 300 years. Kind of hard for us to deal with that thought. A 300-year drought. So what do? You move. There's nothing to eat, nothing will grow, you move. The only place left to move in those systems was to the river valleys, the last place that had water and where things would grow. Cities originate in what we now see as desert regions in the river valleys, and they come about through a process of nucleation. That's just the density of people moving into this area. They already knew how to build. What we start to see then is the beginning, this is not working anymore, or I'm pressing the wrong thing possibly, of more complex social organization. It starts to be a lot more hierarchical, and we start to see the linkages between things becoming more complex. Topologically, we're not very far removed from this now. More or less you can argue that this, topologically, is a system that's spread over the entire surface of the Earth. Multiple connections, some local, some between major centers. In this diagram, which I may not have made exactly right, there's a scale differentiation between the largest artifact in the center of each territory. And there's some peculiar kind of biological and linguistic laws, and not all of them verifiable, but about those size relations. More or less we think of them as a kind of hierarchy. So pretty much all cities originated, this is a modern image of course, but pretty much all cities would have originated like this. Close to a river, with beginnings of an agricultural system, and a cluster of kind of courtyards and longhouses. And maybe I should have photoshopped, but you can see actually contemporary city in the background of that. Okay. But the logic is still there. And of course, the river valleys we can see, these are always the locations. So the first cities, if we think about the Nile as a system, is very, very interesting. And in my book I've done quite a lot of detail. But the Tigris and the Euphrates, we also know in India that the Harappan civilization occurred along the rivers. And most intriguingly, this photograph's kind of the wrong way around. This is from the west coast of South America. And we can see what is essentially now a desert, cut by a lot of river valleys. And their cities emerged there too. This is from the mountain above the Shaka Valley. Not many people know about this, only recently excavated. Probably it's about between 10 and 20 years old, the knowledge that in Peru the civilization was as advanced as Egypt or Mesopotamia, and very, very large structures, big organizations. That's what it is today. The same logic that caused cities to emerge is also involved in their collapse. Some remains are still with us. Some people argue this is the oldest known city in the world. I got the pronunciation right. It's Uruk. Is that how you say it? Someone from Iran is here? Yeah? Okay. Okay. Has slightly different pronunciation now. Slightly different. But you can see pretty much that's the city. Later on it becomes walled, but these are typical of the spatial organization. Not an immensely complicated organization. You can see there's a kind of network there. There's kind of one central axis. There's a few leftover spaces. But the hierarchy of the relation of the internal space of the individual dwelling arranged around a courtyard, arranged along a street with these complex paths, is a kind of persistent pattern. And there it is, now called Erbil. And you can still see it's still there. Okay. So this is, I'll go fast through the evolutionary logic because I need to get to the end. And Tony's telling me to hurry up. Okay, so I try and do kind of final part in about 15 minutes. Is that okay? Okay, maybe I just talk faster. Okay. Cellular organization, how it's evolved. These kind of what were, these kind of accidental leftover bits in the first circular organization we start to see are now internal to the house and are forming part of the organization of the city or proto-city. Also, religion and social order grows up and co-evolves with the logic of the movement from the most private interior space to the most public space. Again, its foundation, its original logic, is externalized metabolism. It's encoded by religion as a way of living. Okay. And we start to see aggregations of larger and larger systems. Most of you will be familiar with all this. We enter a kind of familiar territory of architectural education. Thank you. Which one am I? Okay. Okay. And I have to go faster through this. And the other order that evolves, so we have the courtyard, the evolution of the courtyard, and we also have the evolution of the longhouse, which by some kind of convergent evolution also ends up arranged around courtyard spaces. And you can see it's a little map of Chanyang, how that's done. And Beijing, of course, you can see these very familiar patterns now. And there it is. Still visible. It's quite significant that most of the contemporary stuff doesn't seem to have a coherent pattern. And there it is today, looking rather amazing. We also have kind of curious variation in China and Japan, which is super interesting, which is a kind of combination of the circular pit structures and the evolved longhouse into kind of evolved longhouses wrapped around in concentric circles. And these still exist today. There they are. Okay. And what parallels biological evolution and the conservation genetically of ecological and metabolic knowledge is, of course, these systems. Most of you will be quite familiar. You may not know the early part. You'll certainly know the later part. The first kind of encoded writing are transactions. These are actually tax accounts from Mesopotamia. And this is someone promising to give, when the field is grown, the bushels of wheat. It's a food, it's energy. It's a transaction to do with energy. So information systems evolve out of the necessity to record metabolic transactions. I will buy from you in 3 months' time everything that you grow in that field, and I promise to do it and pay whatever it is I'm going to pay. And you can see here the information system, the writing is still very, very close to kind of it's a pictogram. It looks a little bit like the thing it's representing. Later on they get more elaborate and they stop looking like that. This is cuneiform, and you can see the general evolution is taking 18 signs and showing how they gradually evolve and become more and more abstracted. Okay, I won't explain that one, it's quite obvious. Let's find one that's kind of less controversial. So the bowl, it still looks like a bowl and gradually changes and transforms until you get something that is beginning to record the sound of bowl, no longer the object. Phony. And all of these can be decoded. First architectural plans are known to be 4,000 years old, a lot older than I was taught when I came to the A as a student. I thought drawing originated somewhere around 1750, and my tutor said, no, really, it starts with the axonometric in 1920. So it was all complete nonsense. This is the oldest known plan. It's a plan of a temple, and what's encoded around here is the narrative of its building. It's a kind of super specification. If you knew how to read this, you would know how to build that temple. Okay, a lot older than we think. We also, Egyptians, okay? Most of we know from their recorded writings that they did actually have plans and sections, nice sectional elevation. They did them on kind of soft papyrus stuff which rots, and there aren't many known examples. And these are individual pages, sort of A3-ish. You can see this is a kind of massive drawing. This is a specification from Greece. Pretty much everything we think of as the information system for buildings evolves from the simple evolution of language, from recording an image that looks like wolf, the thing you're talking about, or the chair, and gradually encoding that in an abstract way. And the same thing is true of the evolution of information for building systems. And there's lots of kind of fine differentiations, and we won't go through all that. Okay. There are many ruins of what other people call former civilizations. I argue there's only one civilization, that's human civilization. Nobody's excluded from it. This is in China. Some of you from the US might know this. The Anasazi Indians. And perhaps the most scary of all, this is a city from the Silk Road, populated, we think, until quite about 2,000 years ago, maybe a little less. Once, 20 to 30,000 people lived here. Once there was a river, stands of trees, open fields of wheat and barley. There are some who argue this is our destiny. Every previous society has more or less ended in this condition. Every previous human society. And how are we going to do it any differently? Well, complexification. I'll come to that. But what goes along with that? There is no millimeter of the Earth's surface that is not mapped. There are very few parameters of variations in climate, of flow, of energy that are not known. There aren't many places on Earth where you could find what some people call wild. Great deal of the Earth's surfaces is for rice paddies. A great deal of the Earth's surfaces are either engineered by humans or modified accidentally by humans. Almost nothing you can say about the Earth is untouched by humans. And we come back to this. Most of you will be familiar with the arguments about climate change. I'm not going to go into the physics of it. It's all in my book and very well documented. There are lots of models and so forth. These are all the current systems that are known to be either in transition or very close to their critical threshold of change. And the kind of scary thing is how many there are. When you put them all on one page, on one map, there's lots of science papers about each one of these, permafrost, ozone hole, different changes in forests, what's happening in the Sahara and so forth. But the totality is really scary. And what we know about complex systems is that changes ripple through subsidiary systems. A small change in one system will affect the other systems that are coupled to it. The other thing that goes along with that is, I would argue, and maybe not all of you will agree with me, that we have also expanded, as all previous human societies have done, close to the maximum of our capacity to support ourselves. Everything that you had for breakfast was not grown in London or anywhere near it, probably not even in England. You had orange juices and sausage. Maybe the eggs were English, maybe not. If you had orange juice, it's flown thousands of miles to be on your table this morning. When we go for dinner later, almost everything we eat will be from somewhere else in the world. We don't know, and it's not totally mapped, how complex those flows are. But we are, in my argument, very close to a threshold of complexity. And we do know, most of us have experienced some kind of fluctuations in the amount of energy that is supplied to our cities. We've got used to, unlike in previous societies when cities or settlements were bound to their ecological knowledge, almost none of us have ecological knowledge. You know, I can't go out in a forest and say, you know, my son's not very well, I'm going to pick this thing and kind of cure his bellyache, or, you know, we don't have that knowledge anymore. Almost none of us have it. We don't even really know, most of us, how to grow anything. We're extremely vulnerable. We don't even know how to make electricity, so we just plug stuff in. The number of architects who could wire a house is very small. We do know quite a lot about cities. We start to measure, but we have some problems in even saying what a city is. Most of us, if you ask anyone in the government, where is London, how big is it, they're going to give you the administrative city. That is, where the regulations say the city ends. In some countries, the city is only the ancient walls, and everything outside it is the suburbs. But of course that's not true. And the built-up area turns out in most of these cities to be vastly bigger than the administrative city. And that's not even counting where we get all our stuff from. We also know cities that most emissions that are affecting climate come from cities. And more than half the people on Earth live in cities. And we can model kind of various density gradients and so forth. What we don't know is how all of these kind of energy gathering surfaces, how the urban tissues, these kind of greenhouses and open agriculture and these kind of tissues, we don't know very well the paths of the flows between those. So most urban ecologists can tell you how much energy this block used and why that block is a better shape than this one for energy compensation. Most engineers can tell you, yes, if you use these kind of surfaces, we can capture a lot of energy. We can pack a lot of people in these, and we can grow loads of mushrooms and tomatoes and this kind of stuff. What we don't know very well is the metabolic relationship. We don't know very well the relationship of these kind of tissues to each other, the pathways. We also know, when we look for the equivalent of that, we see this. Nearly always infrastructure nowadays divides and separates. And we move things enormous distances at great velocity, huge quantities of things. If that flow stops, we're going to starve. Even if it modifies a bit, we go hungry, or we're cold, or if you live in a hot country. So the metabolic logic and the mathematics that applies to this does not yet been applied to this, or to the design of this. There is a precedent in architecture around about late 1950s, a general idea, and you can tell from the drawing, that you can inhabit and do something with that infrastructure more than just move things. We know it's the 1950s because all that space is given to cars, which are super important in the 1950s, and that much to transit. And, you know, growing is just kind of a decoration, and the rest of the city is kind of around there. But generally, that idea of that the infrastructure can do more than just let the cars move is not completely new. We also know that that infrastructure of movement, even though it's only to do with cars, has a very significant effect. And it's also strongly related to the densities of cities. But we don't really interrelate all of these things, and most of these things is kind of mappings and analysis, may include that and that, but certainly doesn't include any information, and certainly doesn't include water. Okay. This, next 3 slides, are the metabolic pathways in a living system. This is the work that needs to be done for cities. And it takes 3 slides to show it. That's investigation into metabolism and biology becomes kind of serious science around about 1930 and has been continuing ever since. In architecture, it hasn't yet begun. Okay, so, at least for me and for those who work with me in Emtech, we're going to be working on the flow paths and metabolic systems of cities. I don't think in my lifetime this will ever be fully understood and accomplished for cities. Nonetheless, I think it's a really urgent task. And the reason is this. 10,000 years ago, before cities emerged, the fullest system, the founding systemization, it works out that the whole of the Earth in that system could support 5 million people. Most of you come from cities that are bigger than that. That took the whole of the Earth in the founding system, surface of the Earth, to support 5 million people. We're 6 billion plus today. If the UN is right, within 2 generations, that is your children, yeah, and you'll still be alive, you'll be granny, right, yeah, or you'll be mum, yeah, and your mum will be granny. There'll be 9 billion, half as much again. We know more than 50% of the people on Earth now live in cities. There's going to be, for your generation, the need to build 3,000 new cities within the next 20 to 30 years. 3,000 of them. Each one big enough to hold 1 million people. There's never been a time in human architecture when there was such a capacity. This will be, I believe, the primary task for your generation and the generation after. And what I believe is that the key to making those work in the era of climate change, of great energy shortages, of changed ecological conditions, is the metabolic flow and the patterns that arise from that. Thank you.